Welcome to Spring LIB.
In this exercise, we have a ball that's thrown from 1.2 meters above the ground at an initial angle of 35 degrees and with an initial speed vi. And we want to find in question A, what is the horizontal position x at which the ball reaches the ground. So what's the distance between the point of throwing of the ball and the point when it reaches where it reaches the ground in the x direction as a function of vi. So first of all, I've written some equations here in red. So we have the equation for the y coordinate, the x coordinate, the initial speed in the y direction and the initial speed in the x direction. And in order to use these equations, the first thing we need to do is to set up a coordinate system, and I'm going to do it like this. I'm going to choose y to be pointing upwards and the x coordinate to be directed to the right, such that the origin is at the ground exactly below where the point where the ball was thrown, such that y0 is equal to 1.2 meters and x0 is just 0. Okay, so for that reason, what I'm going to do now is to calculate how much time it takes for the ball to reach the ground, and then I'm going to use this information to calculate the horizontal distance x. So first of all, I'm going to use the y equation to calculate how long does it take for the ball to reach the ground. So we have that y is equal to y0 plus v0y t minus 1/2 of gt squared. When the ball reaches the ground, y is 0 and y0 is 1.2 meters. I'm going to leave the units implicit because everything here will be in the international system. v0i is v0 times the sine of theta, and v0, the initial speed, we have vi, so I'm going to substitute it for vi. So I have vi times sine of 35 times t minus 1/2 of g, so it's 1/2 of 9.8 or 4.9 times t squared. So 0 equals 4.9 times t squared minus vi sine of 35 times t minus 1.2. And from here we can find the time t using Bhaskara's formula. So t is equal to vi times the sine of 35 plus or minus the square root of vi squared sine squared of 35 plus 4 times 4.9 times 1.2 divided by 2 times 4.9. And we are only interested in the plus solution because the minus solution yields a negative t. So I have vi sine of 35 plus or minus, only plus the square root of vi squared sine squared of 35 plus 23.52 divided by 9.8. So this is the best we can simplify the time. So now we can use this in order to find the distance x. Remember that x is equal to v0x times t. v0x is vi times the cosine of 35, and t is this thing here that we have. I already put the 9.8 outside, and I'm going to write the numerator, which is vi sine of 35 plus vi squared sine squared of 35 plus 23.52 Okay, and I'm gonna just substitute the cosines and sines. So it's useful to know, I'm gonna write it in blue, that cosine of 35 is 0.819 and the sine of 35 is 0.573. So x is equal to 0.048, that's the cosine divided by 9.8, vi squared, that's actually, I'm sorry, the cosine times the sine divided by 9.8 is 0.048, plus the cosine divided by 9.8, which is 0.084 vi, times the square root of the sine squared of 35, which is 0.33 times vi squared, and 23 plus 23.52. And this is the answer to question A. On question B and C, we have to find what is x for vi equals 0.1, and then for C we have to find for vi equals 100. So for vi equals 0.1, we have 0.048 times 0.1 squared plus 0.084 times 0.1, this times the square root of 0.33 times 0.1 squared plus 23.52, and this is equal to 0.041. And in question C, we have to do the same thing for vi equals 100 meters per second. And in that case, again, we only have to substitute the vi in the formula that we found in equation A. I'm not going to bother writing all the numbers again, but the result is 964 meters. And here, of course, we also have a meter. And this is the horizontal distance. In question D, we have to assume that vi is very small, but it's very small, but it's not exactly 0, but it's close. So it's very much smaller than 1. And we have to show that the equation that we found in question A simplifies. So again, I'm going to rewrite the equation from question A down here. So what we have is x equals 0.048 vi squared plus 0.084 vi times the square root of 0.33 times vi squared plus 23.52. And I'm going to write this equation a little differently. I'm going to pull out the vi. So we have the vi squared, actually. So vi squared, I'm going to factor it out. And we have vi squared times 0.048 plus 0.084 times the square root of 0.33 plus 23.52 divided by vi squared. Okay, all I did was to factor vi out. The equation is the same. But notice that if vi is much smaller than 1, it's very close to 0, then this term here that I'm highlighting in green is much greater than all the other terms. Okay, because 1 over vi squared, if vi is much smaller than 1, is a very large number. So this means that we can simply disregard the other terms, and we are left with x equals vi squared times 0.084 times the square root of 23.52 divided by vi squared. So this is the same as 0.084 times the square root of 23.52 times vi, because the vi squared inside the square root comes out without the square. So x is equal to 0.41 times vi. Okay, so the equation simplifies a lot. In question E, we have to suppose that vi is now very large. So vi is much greater than 1. And we have to find the simplified equation as well. So again, I'm going to use this equation here that I found in question D, okay, because it's again going to be useful. So what we have is that x equals vi squared times 0.048, I'm sorry, 0.048 plus 0.0884 times the square root of 0.33 plus 23.52 divided by vi squared. And of course, if vi is much greater than 1, then this term here is very close to 0, so I can simply cancel it out. And what we get is that x is equal to vi squared times 0.048 plus 0.084 times the square root of 0.33. So this is 0.096 times vi squared. Okay. And again, the expression simplifies a lot. And in question F, we have to plot an approximate graph for the function x as a function of v. So let's scratch it. We have x here as a function of vi. Notice that for vi very small, the function, the x is a linear function of v, so it's going to be just a line. But as vi starts to grow, then x starts becoming a parabola. Okay, it starts becoming a quadratic function. So the sketch of the graph is something like this. It's something that starts as a line and then becomes a quadratic function.